All right, so we're in section 9.5, 9.6, and we're going to talk about polar graphs. All right, so let me grab a piece of my graph paper, and we'll sketch a graph. So the first method that we're going to use is a method that always works for graphing. We can always make a table of values and sketch our graph this way. So what we have, this is our polar graph paper. The circles represent constant radius. So this would be radius 1, radius 2, radius 3, and then we have our nice unit circle angles. So pi over 6, pi over 4, and pi over 3. So instead of having vertical and horizontal marks on our graph paper, we have radius marks and we have angle marks. So we want to, for this first example, we want to graph r equals 3 cosine theta. So our brute force method for making a graph of an equation is always just make a table of values, plot points. So that's what we're going to do. So I'm going to make a table of values for theta, and then we're just going to calculate r. So I'm just going to plug in different thetas, calculate r by plugging the theta in here, and plotting the point. So I'm going to start with, and I'm plugging these into my calculator to get a point. So I'm going to start with pi over 6. So when theta equals pi over 6, I plug that in there, and I get r is about 2.6. So I would go here, when theta is pi over 6, r is 1, 2, about 2.6. So I get a point there in my graph. When theta is pi over 4, I plug that in here, and I get my r is 2.1, about 2.1. So I go here to pi over 4, and r is about 2.1. Plug in pi over 3. Whoops, not 6, pi over 3. And I get that my radius is about 1.5. So at pi over 3, go to 1.5. Roughly here. And then at pi over 2, plugging that in, my radius is 0. So I get a point here at the pole. Then I'm going to keep going so we get an idea of what this looks like. So at 2 pi over 3, when I plug that in, I get my radius is negative 1.5. So I go to 2 pi over 3 here, and I go the opposite direction, 1.5. And then I'm going to plug in 5 pi over 6. When I plug in 5 pi over 6, calculate, and I get my radius is about negative 2.6. So here's 5 pi over 6, and I go in the opposite direction, negative 2.6. I skip this one, so hopefully we can see how this works. And then when I go to theta equals pi, my radius is negative 3. So here's pi, and I go 3 in the opposite direction. So there's my point. And I get a nice circle. So the graph of r equals 3 cosine theta is a circle. And 3 tells us our diameter. And a cosine, when we have just a cosine theta graph, we always end up with a circle that's centered on the polar axis. If we had 3 sine theta, I think we talked about this yesterday, we would end up with a circle that was on the pi over 2 axis. So we can always just plug in points, plot points on our polar graph to get an idea of what our equation is. But being math students, being advanced pre-calculus students, we want to be a little more sophisticated. We want to be able to do something a little nicer than just plotting points. We want to use some more tools. One of the nice tools for using for graphing, we talked about this back in first semester, is symmetry. How do we figure out what the symmetry of a graph is? So if we can graph just part of it, we already know what the other half looks like. So for example, this graph has symmetry about the polar axis, about theta equals 0. If we knew that going in, we graph the top half and we'd know that the bottom half is exactly the same. So that's what we want to talk about next. Questions on how we plotted these points? Okay, so let's talk about symmetry. So our test for symmetry, very similar to our test for symmetry for a rectangular graph. We talked about symmetry about the x-axis, about the y-axis, and about the origin. Same kind of ideas. So we want to talk about symmetry about 3 different important places. The first one about theta equals pi over 2. So the pi over 2 axis, just straight up and down. To figure out if our graph is symmetrical about theta equals pi over 2, we're going to replace our theta in our equation by our pi minus theta, or negative r negative theta. If the equation comes out the same after we make those substitutions and simplify, then we have symmetry about theta equals pi over 2. So that tells us we have symmetry. So this is exactly like we did with rectangular coordinates, where we replaced x by negative x, we replaced y by negative y, and simplified. Same kind of idea. We replace our theta by our pi minus theta, or minus r minus theta. After we simplify, if our equation is the same, that tells us we have symmetry about that particular, this is our theta equals pi over 2 axis. About the polar axis. And remember, the polar axis is theta equals 0. We're going to replace our theta by r minus theta, or by negative r pi minus theta. If our equation turns out the same after we make those substitutions and simplify, then we have symmetry. So we plug those in, plug r minus theta or minus r pi minus theta, plug that in, simplify, and if we get the same equation back out, then we have symmetry about the polar axis. And then our last place that we want to test for symmetry is about the pole. Remember, the pole is the origin. So we want to know if our graph has origin symmetry. To test for origin symmetry, we're going to replace our theta by r pi plus theta or minus r theta. If our equation turns out the same after we do that substitution and simplify, then we have symmetry about the pole. So if the problem asks you, gives you a polar equation and says test for symmetry, or explain the symmetry of this, the graph of this equation, you're doing these tests. They come out the same. Then you say, for example, if you did this one and it came out the same after you did the substitution and simplify, you'd say the graph has symmetry about the pi over 2 axis, or about pi over 2, et cetera, et cetera. So that's a kind of problem that you would be asked to do with these things. But I want to tell you a couple of shortcuts that make our lives a little bit easier. So questions about our tests. These are just like our tests for symmetry about the x-axis, the y-axis, and the origin. All right, so before I tell you the shortcuts, though, before we talk about the shortcuts, I want to give you some reminders that will help you working with this. Back to chapter 4. Sine of negative theta. Is the sine function even or odd? You remember? Odd. So sine of minus theta equals minus sine theta. That's what an odd function is. How about cosine? Cosine was even. So cosine of minus theta equals cosine theta. How about, let's look at the sine of, because that shows up in these tests, sine of pi minus theta. Let me draw a little picture over here. There's theta. Here is pi minus theta. There's pi minus theta. Sine of pi minus theta is, we're talking about the y coordinate. Sine of theta, they're the same. And then cosine of pi minus theta, the x coordinate. This one's positive, that one's negative. And then let's do two more. Sine of pi plus theta. So here's a picture for this one. Here's our point, here's theta. And here is pi plus theta. So sine of pi plus theta, the y coordinate. They're opposite. This is positive, this is negative. And the cosine. This one's positive. That one's negative. So those little reminders will help you out when you're testing, you're doing your test for symmetry. We plug in those tests, then we simplify, and we see if our equation is the same. But we have a couple of shortcuts, some nice shortcuts. Often our equations just have a sine theta or a cosine theta, or some combination of sine thetas or some combination of cosine thetas. If we have those, if we have our graph of some function of sine theta, so if our polar equation only has sine theta in it, it's going to be symmetrical about pi over 2. So I'm going to say pi over 2 symmetry. So anytime we have a graph of a polar equation that just has sine theta in it, sine theta, r equals sine theta, r equals 2 plus 3 sine theta, r equals 2 sine theta plus 3 sine theta, something like that. Just making these up. It just has a sine theta in it. It's going to be symmetrical over the pi over 2 axis. And if our graph is just some function of cosine theta, just has cosine theta in it, it's going to have polar axis symmetry. So that equation that we graphed, r equals 3 cosine theta, we go back there really quickly. Just a function of cosine theta, so it has polar axis symmetry. So we would have known that going in. We would have just graphed the top half of it and known the bottom half was exactly the same, because this is a function like this is always going to have polar axis symmetry. So those two shortcuts help a lot. We just have a sine theta, pi over 2 symmetry. Just have cosine theta, we have polar axis symmetry. And most of the equations that we're going to work with are going to be just a sine theta or cosine theta. We'll look at others, but most of them are going to look like this. All right, so let's use this idea and let's sketch another graph. All right, questions so far? Okay. So let me grab another piece of graph paper. So let's graph r equals 2 minus 2 sine theta. All right, so we look at this one. This just has a sine theta in it. So what kind of symmetry is this graph going to have? It's going to have pi over 2 symmetry. So if we can graph just one half on half of the equation on the line pi over 2, we know what the other half looks like. We can just automatically fill in the other half. So let's start making our table. Let's do a theta and an r, so we can make a table of values. And we're going to start out, let's start out at theta equals 0. At theta equals 0, we plug this in and we get r equals 2. So theta equals 0, r equals 2. So I'm right here. When theta equals pi over 6, I'm plugging in and calculating. Theta equals pi over 6, I get r equals 1. So here's my pi over 6, and here is 1. When theta equals pi over 4, we plug that in, we calculate 0.59. So here is pi over 4, and we're at about here. And then at pi over 2, I get r equals 0. So this graph over here does this, and we know it's going to do the same thing on the other side. It's going to be symmetrical. So we would end up with on this side, our graph would be symmetrical. And then I'm going to graph this half, and then we can sketch in this half. So when theta equals, find my place. When theta equals pi, we already have that. We're right there. So let's go to 5 pi over 4. When theta equals 5 pi over 4, my radius is 3.4. So here is 5 pi over 4, and there's 1, 2, 3.4. So the graph's going to go like so. And on this side, it's going to do the same thing. So I'd be at about here. And then at 4 pi over 3, I get a radius of 3.7. So here's 4 pi over 3. There's 1, 2, 3.7. So it'll be about here, and go to the same place over here. I know my graph isn't perfect on both sides, but we give you the idea. And then when I get down onto the negative pi over 2 axis at 3 pi over 2, my radius turns out to be, sine of 3 pi over 2 is what is it? What's my y coordinate down here? Negative 1. So my radius turns out to be 4. So I end up with this point down here, like so. And this shouldn't go down below here. So there's a rough graph of that polar function. This is called a cardioid. Cardioid is heart-shaped. It's a little heart-shaped graph. And graphs that look like this, 2 minus 2 sine theta, or 2 minus 2 cosine theta are always cardioids. And we'll talk about some special polar graphs in a little bit. So that's how we can use symmetry to help sketch these graphs. It lets us only plot points for half of it and figure out the other half. All right, questions there on our symmetry. Okay, I want to talk about a couple of other tools that we can use for sketching graphs. Then I want to talk about some special polar graphs that we should become familiar with. And then we'll talk about using our calculator. Because our calculator do some nice things with polar graphs. A couple of other things that we can use to help us graph polar functions is maximum R values. So maximum radius and zero radius. So it can be helpful to plot our graphs, to make our graphs, to figure out when the radius is going to be the largest and when the radius is going to be 0. When the radius is 0, we know we're at the pole. So if we look at our function and we can figure those things out, that'll help us figure to know, okay, this is the biggest the radius is ever going to be, and at this theta value, I know I'm going through the pole. So I just want to do an example of how we would calculate, how we would figure that out. So what is, for this example, the maximum radius of R equals 2 plus 2 cosine theta. So when we see a problem like this, if we were wanting to sketch this, and we want to know when is the radius the biggest, what's the largest that our cosine function ever gets? Cosine goes between what and what? What is it down here at the bottom? -1 and 1. So the biggest this radius is ever going to be is when the cosine of our angle is 1. Because anything else where the cosine is less than 1, we're adding something smaller here. So this is going to be the biggest, largest, when cosine theta equals 1. When is cosine theta equal to 1? Theta equals 0. When theta equals 0, cosine theta equals 1. And when cosine theta equals 1, R equals 4. And this turns out to be a cardioid. If we graph this out, this would be a cardioid that would look like this. And when theta is 0, our radius would be 4. So this is a cardioid with polar axis symmetry. How about the points on where's r equals 0 for r equals 2 sine theta? First off, what kind of symmetry does this graph have? Pi has. It's symmetrical about the line theta equals pi over 2. This has pi over 2 symmetry. Radius equals 0. What's going to make the radius equal to 0? When sine theta equals 0. When is sine theta equal to 0? Theta equals 0. Sine theta is 0 at theta equals 0. And pi. So this would be a circle. And our circle would start out here at 0. It would go up like so. And then when theta equals pi, it goes back to 0. So we get a circle with pi over 2 axis symmetry, starting at 0 and going from 0 back to 0 when theta equals pi. So knowing just a little bit about these polar equations can really help us sketch graphs. And we can know when the radius is the largest. So using that same idea here, when would the radius of r equals 2 sine theta be the largest? When sine theta equals its largest value? Yes? Sine theta equals 1. And when is sine theta equal 1? Theta equals pi over 2. So right here on the pi over 2 axis, our radius is 1. So just knowing these couple of facts and knowing that this has pi over 2 symmetry, we could sketch a graph of r equals 2 sine theta. So that really helps us out with sketching these graphs. All right, questions? Questions so far? Okay, let's talk about some special polar graphs. And then we'll use our calculator. These are in your book. I'll put the pictures up here. You will also find pictures of these in your book on page 667. Let me grab the first set here. The first set are circles and lemniscates. So we've talked about these already. Anytime we have a graph of r equals a cosine theta, we're going to get a circle. Functions of cosine theta have polar axis symmetry, so we're going to get a circle. A tells us the diameter of the circle. R equals a sine theta, we get pi over 2 symmetry. A tells us the diameter of the circle. So those will always give us circles. Lemniscates, we're going to have an r squared and a sine 2 theta or cosine 2 theta. And we get this figure 8 shape. The cosine lemniscate has polar axis symmetry. The sine lemniscate is rotated by 45 degrees. And that's because sine 2 theta is 2 sine theta cosine theta. So we get sine thetas and cosine thetas mixed together. So we don't have pi over 2 symmetry. This one gives us origin symmetry or polar symmetry. You get symmetry about the pole. So those are circles and lemniscates. So what I would expect for these special polar graphs, you can see them on page 67, is that you would, if you saw an equation, r equals 3 cosine theta, you would know that that's a circle, and you would know that it has polar axis symmetry, etc. Lemniscate sine 2 theta, you know it has origin symmetry, or polar symmetry. Same with it. So that you recognize the form of the graph, not necessarily that you could say exactly what the sizes were, but you could use that and come up with have a good idea of what that graph is going to look like. So let me grab a couple more. These special polar graphs are really nice. The next ones are our limasomes. So there are limasomes. So we graphed a cardioid. A cardioid is a special type of limasome. And what determines whether the limasome has a loop, or it's a cardioid, or it just has a little dimple, or it's kind of straight, is the relative sizes of A and B. And it's not necessarily that you memorize those relationships. If A and B are both the same, you always get a cardioid. And depending on their relative sizes, you get a loop, you get a dimple, or you get just a straight side. So anytime you have an equation where you have an A plus or minus B cosine theta, you're going to get a limasome. Your limasome is going to have polar axis symmetry. So this would be a cosine limasome. This would be a cosine limasome. If you have A plus or minus B sine theta, you get a limasome. That's going to have pi over 2 symmetry. So if we rotated these 90 degrees, we would have sine limasomes. So I'd expect that you would recognize that R equals A plus or minus B cosine theta, some kind of limasome, and what kind of symmetry it would have. So you could come up with an idea of what the graph looked like. And then you could plot some points and be able to get a pretty good idea of what the graph looks like. And again, page 67 has all these. And one more set. These are my favorites. Favorites are the easy ones. These get the polar graphs are pretty interesting, some of these. The rose curves. So a rose curve, you're going to get a rose curve anytime you have cosine of a multiple of theta. So 2 theta, 3 theta, 4 theta. When you have your function of the cosine of theta, you have polar axis symmetry for your rose curve. Sine theta rose curves are going to have pi over 2 symmetry. If n, the number in front of our angle, is odd, we have the same number of petals as n. If n is even, we have twice as many petals as n. So here, this would be n equals 4, and we end up with 8 petals. And A tells us here kind of the diameter of 1 petal. So again, I would expect that you could recognize the form of a rose curve, what kind of symmetry it had, and then come up with a reasonable looking sketch of the graph based on what we know. And again, these charts are in your book on page 667. All right, last thing I want to talk about, calculators. So let me pull this up, and we'll talk about how we do these polar equations in our calculator. All right, so we're going to go to our mode button. We're going to hit our mode button, and we plotted. When we talked about our calculators last time, we plotted parametric equations. So we went over here to where it says function. We went over to parametric. Now we're going to go over to polar. That's POL means polar. So there's our polar mode. Hit enter. And now, when I go to y equals, it says R1, R2, R3. And then I just enter my equation, just like we've typed it out. So let's do 2 plus 2 sine theta. I hit enter. Whoops, I hit graph. And there I get a cardioid. So it graphs my cardioid for me. Now it looks stretched out on the screen because the distance here in my x's is a little bigger than the distance here in my y's. So it kind of stretches it out. And we can set the window depending on how big. So what I'm graphing here is between 0 and 2 pi. And x is going from -5 to 5, and y is going from -5 to 5. And I can graph all kinds of polar equations here. So we could graph a rose curve. So let's do 3 cosine 3 theta. Graph that. So it graphs a nice rose curve for us. And we could graph, let's graph one more, let's graph a sine rose curve. So let's do 3 sine 5 theta. Or let's do 6 theta. Graph that. So we get this rose curve with 12 petals. And a nice little flower. And let me go back really quickly here. Let me go to the y equals, and let's do a nice and easy rose curve. Let's do 2 theta. Notice how this is graphed out when it sketches it. You can see how it's sketched out. Notice it doesn't make one petal at a time. It makes a part of the petal, so it's doing kind of a loop-to-loop as it sketches that out. And that's how our radius varies. Our radius changes as our angle changes. So it doesn't do one loop at a time. It kind of does this figure 8 thing. Kind of interesting. So our calculators will graph these out. So some of the problems will ask you to graph them by plotting points. They'll ask you to graph them in your calculators. So you can do either way. All right, questions? All right, homework. So I think that's the bell for a regular Thursday. Today we get out at 6.
We get out at 10 minutes.
Yeah, it's at 2:15. All right, there you go.